Hi and welcome to FBDs This is going to be going over practice problems for topic 4, trusses, machines, and distributed loads. And I thought that I would go over the 2019 test number 4. This is back when the course had tests, which was on, at the time, distributed loads and machines. Now we still have trusses and frames dealt with in there, so this is a good question that gets to the same point as the course has gotten to this week in 2020. Okay, so what we're going to do is consider the following structure consisting of members ABC, members C, D, E, F, and E, G, and BD, along with pins at B, C, and D, and an external fixed support at point A. And we have external loads applied at point F, and a distributed load along EG of W at Y. Now the objective is to draw free body diagrams for all the frames and pins which aren't 2-force members or 2-force pins, and then find the forces and moments applied to all of those frames. So let's start off with the free body diagrams. We need to draw this for anything which is not a 2-force member or 2-force pin. So let's have a look. This thing BD here is a 2-force member because it only has forces and no moments applied at each of the ends. So this is going to act like a truss. So we're not going to draw a free body diagram for that. So what about the other things? Well, this definitely has a distributed load on it, so it's not just a 2-force member. C, D, E, F has the reaction force and moment here, and the force there, and forces there and there. So lots of forces on it. Same with A, B, C. So okay, we've got to draw it for all of those different points. Maybe we should put in the coordinates of points on this, if that way we won't have to write them more than once. Okay, I think we're okay. We can put them in better spots if we put them in after. Okay, so we'll copy that and put that down there. And then we're going to need a copy of this member, which we can put sort of over here. Yeah. Maybe there is better. Okay. And then this one, maybe we'll put the y-axis in that as well. Okay. And we're going to need, that's it. I guess the force at F is applied down. Okay. So now we've got the thing split apart. We're going to draw three different free body diagrams. And to draw these free body diagrams, we need to label all the forces acting externally on these things. So at A, we're going to have a force there and a force there, sure. And this is going to be AX and AY. Then what else? We've got the reaction from C. So we've got the X forces, CX, and we'll have a force in the Y direction as well. It's arbitrary what direction we put this. Let's go like that. CY and CY there. Newton's third law, action-reaction pair. So this represents the Y, the force in the Y direction that CDF is putting on ABC, whereas this one would be the force in the Y direction that ABC is putting on CDF. So that's why they're equal and opposite, and same thing for the X forces. BD has, being a 2-force member, we know already that it's going to put a force in the direction that is acting between the two pins there. So this is force BD. We can figure out the direction of that by looking at where the coordinates of those pins are. At point E, we have, oh, actually, before we go on, I don't want to forget that we have a moment applied at A as well. Maybe we'll get a different color for moments. Yeah, that'll do. Some moment magenta there, MA. And again, it's arbitrary what direction you choose as long as you're consistent. So here at E, we've got a moment like that, and then we'll put it the other way on this one. Be careful to check that it makes it spin in the other direction when you apply this moment. We'll call this ME. And then we've got some forces, right? we've got a force in y. Let's put it kind of like that. Sure. EY, EY. And that's going to be 0 because there's nothing putting a y force on this. But we also have an x force. And we can guess what way that's going to go by what way it would have to go to counteract w at y. So let's put that to the left, and remember that we did bother to assign that in the direction it probably is. So over here, it's going to be to the right then. EX. Yeah, another way to look at it is the effect of this distributed load is going to create a force to the right on CDEF. Yeah, okay. Finally, we have a force down at F, which is 1, not italic now, because it's not a variable, 1 kilonewton. So the next thing to do is to label the points. I like to use green for that. So let's go with a label down here at the bottom. We said A is at 0, -2. That's point A. Then we got point B, which is at 0, -1. And then point C is probably 0, 0. Yeah. And that's convenient that this is where we put the 0 for y, so that the w at y can start at 0 at this spot. Okay. So then point C is also 0, 0. Same point here, just on the different diagram. Point D is 1, 0. Everything's nice round numbers this time. E is 2, 0. And point F, 3, 0. Yep. Amazing. Let's put this on the next line so we can see it all at the same time. Point F, 3, 0, and point G is 2, 1. Okay, and we'll also put our 2, 0 label there. Yeah, all of this in meters. Okay, so there's our diagrams, our set of free body diagrams for this combined object there. How to copy the whole thing? I can use the other select and make sure not to include that top diagram at all. And there we go. Okay, so here's our free body diagrams copied in. And now we're in a position to go and apply Newton's second law on each of these different objects to generate our different equations. Each of these 3 frames is going to be subject to 2 force equations. The net force in X and net force in Y are equal to 0, and 1 torque equation about any point that we like, which is convenient for eliminating the unknowns. So none of those equations are going to be trivial for any of these because we do have forces in X and Y, and the possibility of torques produced about all of these things. If we had a 2-force member that we didn't recognize, it would have just given us the fact that BD, that the force at each side of these pins are equal and opposite, and that they end up being collinear. But we've already incorporated that into this. You can see the angle maybe a little bit better here. If this is 0, -1, and then we've moved 1 over to the right to go to 1 something, and we've moved 1 up to go to something 0, then this is a 45-degree angle. So it's our familiar 1 over root 2 when we take the horizontal and vertical components. So let's start writing them. We've got our maple open here. We'll restart, and then we'll just go kind of one at a time, write out net force in X is 0, net force in Y is 0, and net torque about some convenient point is 0. So we can maybe set these all up in an equation at the start. So let's go for the object, the first frame over here, ABC. And the net force in X will have AX to the right, plus BD over square root of 2, plus CX, and that's it. Net force in, so this is equal to 0. We've added up these 3 forces, and they're going to be equal to 0. When we just give one side of an equation to solve, it assumes you mean this equals 0. That is required because this isn't accelerating in X, so we have no net force in the X direction. Okay, in Y, we're going to have CY plus BD over square root 2, the Y component of BD, minus AY. And now for the torque, we can take it about any point we like. Maybe the bottom is the easiest. So, yeah, that's okay. So about the bottom in the, what are we going to say is positive? The out of the page direction, the counterclockwise. So we'll say MA, because that's now in the positive direction for that, positive being this way, counterclockwise. MA, BD is also going to be creating a positive one. BD's X component, which is 1 up, 1 times BD over square root 2. And then CX is creating 1. Oh, but wait a minute. Hold on a sec. BD's X component would create a negative torque because it makes this move rotate in that direction about point A. So actually, we should be subtracting that. Minus BD over square root 2 minus CX times 2. Now, just as a check, if these were both positive, then you would need MA to be positive as well, and that makes sense. So the more positive CX and BD are, the larger, the more positive MA needs to be as well. To counteract it, it agrees with what we have in the picture, so the equation looks good. Now, moving on, the next beam, CDEF, we can write as well, using the same idea. Net force in X would be minus CX minus BD over square root of 2 plus EX, and that's it. In the Y direction, we'd have minus CY minus BD over square root of 2 minus EY minus 1E3. Yeah, so this force applied at the end. Maybe we'll call that FF or something, the force at F. Minus the force at F, okay? And now the torque equation. Again, we can do torque about any point we like. Maybe left end is easiest to think about mentally, but totally up to you. So about the left end, we'd have a negative torque from BD. That would be a clockwise rotation. So minus 1 away times BD's Y component. Then minus 2 away times EY. EX doesn't create any torque there. ME is also in the clockwise direction because of the way that we wrote it here. And so is the moment created by this force here. So minus, let's see, how far away is that? That would be 3 away, 3 times FF. Remember that the moments, we don't care about how far away they're applied. They're already in a pure torque sense. This is really caused by a couple created in the joint, and that creates the same torque about every point that we go and calculate it. So as you can see from the Y equations here, given that everything is subtracted, some of these things are going to end up being negative. Again, don't go back and reassign them or resolve the problem. It's okay if they're negative. That's fine. It just means that the force is actually in the opposite direction to what we showed. Same thing with the moment equation. Because everything is subtracted, something in this thing is going to be negative as well. Now, we already know that some of the BD, CY, EY, and FF have to be negative. So it might be that ME ends up being negative. It might not. We can make a prediction at the start. It looks like ME has to be positive because just from EG, if W at Y is positive and pushing to the right, we're going to need ME to be positive to counteract that. So this is positive, which means further some of these other things in here like EY, well, EY is going to be 0. So the only, and FF is not positive, or is not negative because that's known, which means definitely we can say for sure that BD has to be negative. And that means that this is not in tension. It hasn't been pulled apart. It's in compression. And that makes complete sense, right? Look at this. We're pushing this there. We're pulling that down there. This has got to be in compression. So BD is going to be probably quite large to counteract the rest of the stuff that's going on and compressive, pushing back out. Okay, let's write the last equation here. So for EG, we are going to have, and this is the trickiest one. It involves the distributed load. Net force in X would be minus EX plus the net effect of this entire distributed load, which is the integral of it, integral of W from Y equals 0 to 1. Yeah? And we're going to need to define what W is. Let's put it up at the top here. W is equal to 1E3. Conveniently, they just gave it to us in this question. We don't have to look at the picture and try and find an equation for it. 1E3 times 1 plus Y minus 0.5 all squared. Okay, so there's our W. Yeah, where the Y was defined as given in the picture, where it starts at 0 at this point. Okay, good. So there's the net force in X. Net force in Y on this is just EY, and that's how we knew that that was going to be 0. And the torque, let's find the torque about the bottom point. That will be in the counterclockwise direction, ME, minus the integral of y times w from y equals 0 to 1. Why is that? A little bit of force over distance dy of this would be dy times w at y, and that's how we're going to integrate to add all those up. And that creates a torque about point E, which is in the opposite direction, and given by the y coordinate multiplied by that. So y is the distance away from point E. Conveniently, E is at a y of 0, so we don't need to subtract anything else for this moment arm part of it. And the force comes from this times the dy in the integral. So we've been consistent to make it obvious what is what and help us sort it out later. It goes force in x, force in y, and then moment about some point. Force in x, force in y, moment about some point. Force in x, force in y, moment about some point. We can put in, we need a comma there. That's just that would have caused us some trouble later. We can put in, so I'm using Shift Enter to go to the next line, by the way, when I go from here to there without executing it. We can put in a comment with the hashtag thing there and say what this is. This is torque on ABC at A. Yeah? And this one is the torque on CDF at C. And this one is the torque on EG at E. Right. Okay. So now that that's done, we can close off that bracket and execute the solve command, and we get an answer. We have a unique solution. No parameters unsolved for, and no lost output. It gave us an output, which means that the problem seems to have a unique solution. Now we do the part that is easy to skip. Once you finally get an answer and the code gave an output and you're like, yes, it worked. No errors, right? Well, there could be logic errors. So let's check if this makes sense given the ways we defined it. So MA is indeed positive. We made a prediction earlier that BD was going to be negative and large, and it is negative and quite large compared to the force that we applied because it has to deal with the distributed load, which is having a net effect of EX, and the fact that it's kind of up high, leading to MA being quite a large thing. A little bit surprising, I suppose, that MA is so much larger than EX needs to be. So I'd want to double check that. We're integrating Y from 0 to 1. And what's up with this distributed load? Is it actually like way bigger at the top? Suppose it was all at the top, right? It was a net effective EY of EX, 1000, totally at the top here, which is at a location of 1. This is very weird that it gives that much of that it requires that much of a moment to counteract it, because it should just be that force as a point force even. Like it's not quite that much because it's distributed over this. This 1083 applied right at the top, right? Unless this thing is sometimes negative over the range that we've got, but nope, it's positive definite. So very odd. What's going on there? Why is MA? Oh, that's MA. I'm reading the wrong one. ME, yes. ME ought to be less than just 1000 times 1, and it is. MA is really large. Why is that? Okay, we got this effect, which is like 500, and then the 1000, which is 2 over, that's like another 2000, so we're at 2500. And then this one, 1003 over, that's like 5500, and that's where it comes from. So there's the external force applied on like this object, leading to MA being on the order of 5500. Okay, AY is negative, meaning it's actually pushing up. That's because this one's pushing down by 1000, so we need to counteract that by pushing up on the whole thing by 1000. Yeah. So CY is actually positive, meaning we're pushing up here, we're pulling up on this there because BD is pushing with this 5000 force. It needs to be that much to counteract the moment applied by these things on CDF to stop it from rotating about point C. Okay, so there's a bit of a sense check and a talk through how to do statics problems in 2D involving things like two force members and dealing with things like distributed loads. Thanks for watching. I'll see you next time.